Hello and welcome back everyone. After about a year, or was it 2? I forgot even. Anyway, this is our hacking sessions on the oreboot project, and oreboot is firmware written in Rust, and I just realized that we're actually missing a title down here. So let me quickly add that. And so today we will be working on an SoC, a system on a chip that is called BL808, and we're going to use a development board called OX64 from Pine64. And yeah, that is a very prominent vendor, and also now a more or less prominent board featuring this SoC. So BL808 is from a company called Bouffalo Lab, and we've actually already done 2 live streams before on that one. Yeah, but it's been a few years, and yeah, I sort of promised we would be getting back to it. So yeah, let me just finish up the title down here, and there we go, oreboot on BL808. And today we will be initializing something that is called PSRAM or pseudo SRAM. That would be sort of DRAM, so dynamic random access memory. And that means that we get to use a bunch of megabytes of memory actually. In this instance, that would be 64 megabytes. So yeah, let's actually have a quick look at the wiki here. This is the Pine64 wiki on wiki.pine64.org. And yeah, as usual, I will just put all the links in the show notes again later on. The recording will be uploaded again to YouTube as usual. And yeah, let's dive right into this one. So this SoC here, BL808, is featuring 3 cores actually that you can program. One of them is an E907 core. That is the initial core. That is where the maskram is executing the first code. So that would be the code that is actually baked into the chip and that you cannot actually change in any way. There is another small core which is called E902. So both of them, starting with an E, they're of the same sort of family, if you will. They're in the microcontroller range. They're both 32-bit CPU cores, as they write here. And then we have another core, which is a C906. And that's a 64-bit core. And the C cores, they're actually made by a company called Xuantie. That would be formerly T-Head from Alibaba. And, you know, they are one of the main vendors of RISC-V cores nowadays. The other one being Sci-Fi, which we've also featured here. And I've actually been to the RISC-V Europe Summit last year and met some people. So yeah, as you may guess, I also got some gadgets and stuff, and that would be including this pen here. So yeah, thanks a lot. I'm actually a big fan of those cores, if you didn't know. And that is mainly because they actually were the first one I worked with. That is one thing. And on the other hand, I realized that, you know, cores can be different, right? And some might actually have, you know, certain features and others don't. And the Xuantie cores in general are handling unaligned access right in the hardware, so I don't have to do that in software, or anyone else for the matter, which is an issue that we actually had with, you know, the Sci-Fi cores. It's not a big issue usually. That's not what I'm saying. But yeah, it's a bit less work for me if I don't have to deal with that. Anyway, so let's see where we're at here. So this thing here, as you can see, is a very small development board. It's actually not that large. I have it connected here on my table already, so yeah, I can show it right now. We've had a look at it before, and this was actually a gift from Pine64 themselves when I met them at FOSDEM 2 years ago. FOSDEM being the large free and open source software developers meetup in Europe. And that will actually be happening again very soon, in 2 weeks already. So it's always the first weekend of February. Anyway, so with this thing, we actually got just a few first steps done initially. So the BL808, was a bit of a mystery to us initially, so we had to explore a bit. And over the last 2 years, we've actually done a bunch more work on the oreboot project, but also get back to this very SoC here. And just over the last few weeks, just because I met somebody who was interested in it, together we developed a tool for it that would allow us to load code into the chip, which we've actually done before, but this one now is a bit handier. And best part of it, it gives us some more control. And, just by writing the code ourselves and getting to know the protocol and stuff, we actually now are able to run code on any of the 3 cores just as we like. So what I've done now is I've prepared a setup so that I can just run one command and that would load the code and already give us a console in return. And I can run code on the C906 core right away. So before that, what we were doing was we were running on the E907 core. Then we were, also having some code loaded already. And we would then tell some, there are some registers that you can figure. And we were telling them to actually, point to a certain place in memory for the C906 core and start executing its code. So yeah, that was, a bit finicky. And as it turned out, not actually necessary. This chip is actually featuring so-called fuses. So we briefly touched that topic in the previous streams. And with those fuses, you can configure the SoC to behave in a certain way. And you could technically even boot it over USB if you wanted. However, unfortunately, that is broken with the MASCRAM version that we have in this board here. So if you buy the newer versions of the SoC, you might actually, get a different MASCRAM on it that is then capable of booting from USB. So we will still be booting over serial here. Anyway, so with all of those words, let's actually have a look at that, right? So I have prepared something here. We have a makefile now in our oreboot fork. I just rebased the branch we had been working on, and cleaned up a few things here and there. And we will now be running some code on the C906 core right away. And then we will get some output from it. So let's see how that works. We just run make run here. And by make run, we will be running that, tool we just created. I will also show that in a bit. And then we will attach right away using PicoCom. So PicoCom or Minicom, we've used those tools before. That is just for connecting over serial, and then we can interact with it. So we can send out data, we can receive data, and because we're just retrieving text here, that's all we're doing. That is actually a very, very neat tool. So let's have a look at what happens here when we run this command. You see there is actually an error happening, and that is because I haven't actually powered on the thing. So what I need to do now is I need to press and keep held the boot button. Let me quickly show that actually here. So the boot button is right here, and then I will be supplying power from here. And fortunately, I have a USB hub which has, individual switches for each and every port. So, I will just be powering on this SoC now. And lo and behold, the next invocation of the command didn't actually work. I was a bit too fast. Oh, we're getting timeouts. That might actually happen. I think I haven't pressed the boot button long enough. Yeah, it's been a while since we've been doing this, so yeah, let's try again. Ah, there we go. There we go. Now it works. Okay, so I'm going to terminate this now because it would otherwise infinitely be outputting lol here, which is sort of funny, but it's not our main goal. So let's scroll up a bit and see what happened. So the first thing, you see some output from up here that is from our oreboot build process. Just neglect that part for now. It's not too important here. What interests us is this here. So we're running this tool here. We called it BL808, BL for Bouffalo Lab, and then boot for booting something. We give it the port that we want to use. So in this instance, it's the TTY USB 0. And we send it 2 files. The first file is empty.bin. That is really just an empty file. I just needed to put at least 1 byte in it so that the chip would accept it. And we're sending that over for the E907 core. However, there is nothing in it and we're not running it. And the other thing we're sending is our firmware build for the C906 core, which is this year. Yeah, I don't really know how these quotes here happen. Yeah, I think it's because I'm a bit messy with makefiles and actually not too sure when or where to quote things. Whatever. So we're sending over this bin file now. So the tool is now giving us some more colorful and structured log output, and it's saying which port it's using. And the first thing we're seeing is, oh my, an error happens. However, this has been happening also with the other tool we've been using. That was Samuel Holland's Bouffalo loader, and it was also happened with a vendor tool, I think. And that is really just, I think there is some sort of automatic baud rate detection going on initially, and that just takes a while. So we just run the same code again over and over until it works. And usually it works on the second attempt. So when we scroll up from the earlier attempt, we can see, it actually tried a few times and said, well, we're getting timeouts here, nothing is happening. So yeah, with that said, so the next thing that would be happening is we now need to send a handful of headers. So the first thing would be a so-called boot header. That is actually a very, very large block of data already. It's a few hundred bytes, and that includes a lot of configuration. That is unfortunately quite a lot, so that is also why it took us a while to get the tool done. I mean, we sort of got it done quite quickly, but yeah, it was still quite a lot to do. Anyway, so yeah, with the boot header sent over, we now need to send a header for each of the binaries that we're loading. The vendor is calling it segment, so we just keep the terminology here. So we also call it a segment. In our instance, a segment is really just a flat binary. That's what we built with oreboot. Yeah, the first one, as I said, is really just a few bytes. We could technically also omit that. It would just, require working a bit more on the tool so that, you can say, hey, use this binary, run it on that core, and don't run anything on that core. Yeah, it's just the way it is now, and it's simple and good enough for us. So yeah, as you can see, it's really just 5 bytes. Anyway, so the header here is actually very simple, and what you see here is actually the full segment header. So you give it an address, a size, then just some zeros, that is just some reserved bytes, and then you give it a checksum, so that would be a CRC32 checksum, and that's already it. And right after that you would send the first segment. So we're now sending the data here, and what the chip is now doing on the other side is it's checking whether this checksum and the expected size and everything actually fits with the data we're sending over. So after 5 bytes, because we're saying it's 5 bytes in size, which are written to this address and memory, we'll then see if this is actually the checksum of those 5 bytes. And well, we're doing this with a second segment now, and that would be the code that we're actually running on the C906 core. And as you can see, it's a bit larger. So the size here is 1BA0. Well, this is hexadecimal, so let's actually see what that means using a modern calculator. And hex 1, come on, 1BA0 is, well, 7 kilobytes roughly, right? So yeah, having sent that, we then send another command, which is the check image command. I'm not sure if this is actually necessary, so it's also what Samuel was doing in his tool. It could be that we may also just skip it. This is then, I think, checking for another checksum that we sent earlier. Well, it's actually a hash. So part of this boot header here, the big one here, is also a SHA-256 checksum, and well, that is actually a hash, right? And that is how the maskROM, or well, the code in the mathroom can now check whether what we sent was actually, fully okay. So we sort of have a double check here. I mean, we already have this checksum here. But this checksum, oh, now I remember, I just confused a few things. This checksum is really actually just for these few bytes of data here. So it's really just for the header itself, which makes sense because you really don't want to get the address wrong, for example, or the size or something, right? So you want that to be consistent. So by the way, the boot header actually also has a CRC32 checksum in the end. Anyway, so the last thing we're saying is run image. So that is the last command. And lo and behold, our code is actually running. So when we attach the serial, we could already get our first output here. So we're getting our friendly oreboot. We get a crab emoji and, then a bunch of information read out. And you might notice we're printing something that you might have heard before. It's actually what you see here on the right-hand side. So this here PLL or phase lock loop, that is part of a clock setup. And we're just adjusting the configuration step by step here. And we're doing that based on the vendor's implementation, which has been ported over to Samuel's U-boot fork. And we're looking at the code right here on the other side. So on this side here, you can see what's happening. There's a handful of registers that are being changed here. So the first one being the PLL configuration register 1, also what we're doing here, and so on. And we're just adjusting a few bits. I'm not exactly sure what those really mean. So some of them are sort of self-explanatory, like reference clock select something. I'm not exactly sure what it means to select something here. Then there is a div ratio, a divider ratio. That also makes sense in a way. And then there is like some, I don't know what even divider enable means here. I don't know. So the thing is, this is all coming from the vendor's code. And unfortunately, the manual for the SoC does not cover those registers, which means the only way for us to understand it is, by reading the code. And if the code doesn't actually have comments on it, we can't really understand it much more. And if you look at this here and you're familiar with the U-boot project, you will see there are actually hard-coded addresses in here, like this one, for example. So usually you would define like a base register. So that would be, everything just rounded down here. So you would have all of those zeros, and then you would just work with the offsets, and you would use that base address somewhere in the device tree that you then, read from this function here. Well, or your actual entry function, that is the probe function. And let's actually have a look at that and see how this whole thing here starts. So what we're looking at is driver code, and driver code in U-boot is registered in a very simple way. There is this thing here called U-boot driver. You invoke that. You pass it something here. It's called BFLB PSRAM. I'm not exactly sure how that works. It might be that this here is a sort of C macro and then a name being passed or something. That is how I would understand it. And then each and every driver has a name. It has an ID. So this here would be, they have these things called U classes. I think the U would be for U-boot or something. And yeah, that one U class RAM. So because this is initializing something related to RAM. Then we have OF match. OF match is very important. So that is actually what I just mentioned earlier. OF here means open firmware, and open firmware is which, it's an older standard. It's from the early 90s. And in open firmware, they actually describe the device tree, which, is now also a standard, by itself. So it's been extracted from there. Open firmware itself was at some point suspended. But yeah, it's still living on, because it actually sparked a bunch of ideas. So yeah, what this here is doing is it's looking at the so-called IDs. So let's see what those IDs are. We see that's actually this here. And if you search for this in the device tree for this board, you will find it and it would describe something. So let's see if we can actually find this in the device tree. And that is what we would find in the ARC RISC-V and then DTS directory. And as you can see here, there is actually a device tree for the BL808. And yes, we do actually find this here. It says compatible equals something something. Now let's give it some more context. Let's get some few more lines. Let's actually get the lines around it. So let's say -C3, and you see this here. So it says PSRAM UHS. That is now a node in the device tree. And it says it's a memory controller, and it's sitting at this address. So this address is important for us because this is now the base address that we also need to talk to. After that comes the compatible string. So the compatible string is always how you identify, the certain blocks in a processor and or in an SoC. And, then on the driver side, you would then search for that and see, oh, that is something I know. And then you would read the address for it, which is encoded again here. So you have this thing called reg. And the first thing that you get in reg here is the base address. And the second thing would be the size. So this here would be 4 kilobytes or in hex 1000. All right. And this is now what is actually being evaluated in the probe function. So the probe function is the next thing you find in a driver. And well, besides that, you then have another few things. I'm not exactly sure what priv auto is. I think priv is just short for private, if I'm not mistaken. I may be. I'm not too deep into U-boot, so it's really just my layperson's knowledge here applied because I've looked at a bunch of that stuff. So we got this struct here. It's called PSRAM info. That is this thing over here, and you see, hey, there is another base thing. And this is actually where the PSRAM itself starts. So yeah, for whatever reason, it's encoded again here, and that is actually hard-coded. I'm not exactly sure why they're doing this here. And then here it says memory size +1 times 1 megabyte. So I guess that would be 63. And as you can see, priv is actually being passed here. So yeah, I'm not exactly sure how that works. Yeah, we would need to look at the implementation in U-boot that is actually invoking this thing or using it or whatever. Yeah, so this function here, get info, is then part of the methods that we find. So if we look at this here, right? So BFLB PSRAM ops, that is what we have down here. It has this one thing here called get info. Oh, right, yeah. And if we look at this here again, it actually says size of this struct. So this struct here is, this sort of struct here, PSRAM info, and it has a certain size. So, it's just a handful of pointers and values or something, right? So it's not very, very big, but it needs to be kept around in memory for later use. And yeah, that is apparently what is happening here. So yeah, now that we know roughly how drivers work, let's have a look again, how the flow actually is. So this function here, the probe function, would be called for every driver. So you would be probing, and you would see, hey, am I, driver, actually the right driver for whatever I would find on this device here? So let's jump to this function PSRAM probe, and we see this thing here happening. I'm not exactly sure what this here does. So you get this struct pass, which is called uDevice. It's something describing a device. It says def remap adder. I'm not sure what the remapping here means. And then in the next few steps, we already get a few values assigned, and they appear to be hard-coded. So there's some frequency here, some memory size. This here is surely not the PSRAM memory size, but it's like, I don't know, maybe the size of a struct or something. I'm not sure why they're hard-coding it here. I would personally do that. I don't know. And then there's this here, page size. Yeah, no idea what this refers to at this point, right? We might actually be able to figure it out at some point. And then we have these two main functions, and that is also the code that I started translating. So we get this here, a GLB, so that is what Bouffalo Lab call their global registers. It's like, you know, the global configuration registers. Then they have this here, UHS. UHS for ultra high speed. That is what they, you know, use it like as a marketing term mostly to describe their RAM. So, you know, they're saying, hey, this RAM here is so fast, it's high speed, it's ultra high speed, couldn't be any faster. I'm not even sure what that means. I don't know what the exact speed here is. It could actually be this here. Maybe it's 1.4 megahertz. I don't know. Could be. Anyway, so yeah, this function is what we initially had here. And yeah, it's, as you can see, it's really just configuring a few registers, then applying a little delay, and that's already it. And then we already continue with the next function, PSRAM UHS init. And that is where we're going to continue today. So we will be just copying over some more code here. And yeah, that brings me to our oreboot code. So in oreboot, you know, we have two directories here. Let me briefly show that to you. So we have one directory for the C906 core and one for the E907 core. That's what we did earlier. This left over here, loader.py, yeah, that's, as you can see, what we used 2 years ago. So yeah, it's 1st of January 2023. It's 2025 now. So yeah. Yeah, and we just ended here yesterday, and then I added a few more of those register adjustments. So what I'm going to do now as a first measure is I'm going to factor this out, right? So what I'm going to do is I will make this a function, and I will just call it, I don't know, PLL init or something. So yeah, let's go PLL init. So let's create a function for it, and we'll put that in a file that we call init.rs. So we will have a public function pubfun PLL init. We could actually just go PLL, and that is because you know, we will just put it in the init module. So we will be calling init PLL. So we add another module here. We say mod init. There we go. It says file not found because I haven't saved it yet. So I will just save that. And as you can see, it's already complaining. And why is it complaining? It's complaining because I'm using a bunch of constants that are not defined in here. But they're actually in here. So what I'm going to do is I will just copy over all of this stuff here, and everything else is really just leftovers from earlier work. So, whoops. Yeah. There we go. Beautiful. Yeah, we can already remove this stuff here. It's no longer needed. Yeah, we don't even need this stuff here. Yeah, we did want to initialize the UART a bit different and stuff. We just need to keep in mind that the first UART 0 is actually in the par domain of the, oh, that should be E907 core. So yeah, we wouldn't be powering it down. We currently just keep it active. Yeah, if you want to know more about this, you know, just look at the earlier recordings that we did here. Alrighty, so with that, we still need a bunch of utilities that we're using here. So I will be adding that here as well. We say create util, and then we have these functions clearbit, read32, and so on. And whoops. Yeah. There we go. Now we have this whole block here, you know, in its own file, in its own function. And that enables us, you know, to actually keep an overview here. So this here is really just our main function now. It's really just a very, very few lines. All right. And let's also remove this stuff here because, yeah, we don't need it.
I will just keep this comment here. So at some point we wanted to use UR3. We're just not doing it for the time being now, mostly because we don't really have to. Oh, and that would then be C906. So UR3 is in the C906 power domain. So it could technically, turn off the E907. There are some registers that we could use, for doing that. But we're just not interested in that right now. So we just want to work on our PSRAM init. So what we're going to do is we're going to create another module. And that module would be called PSRAM, right? So we create a file, psram.rs. There we go. Now no more complaining. And now that we have called init PLL, well, let's say PSRAM init, right? So now we just need to create the init function, and we do that again by saying pub fin init. And we're actually not doing anything here. So let's just make it an empty line. However, we do still need to do a bunch of import, and we're just, oops, I'm just pressing the wrong buttons here. Or keys actually. So yeah, we're also importing our helper functions here. So those are really just, more handy implementations of, reading a 32-bit value, writing a 32-bit value. uDelay is for, we're just doing a bunch of knobs, so no operations actually. That's how we essentially do the same thing they're also doing here in this other function we looked at. So yeah, it's really just like a sleep function. Anyway, we're going to now walk through the code step by step and just start translating it. So we've done it a few times now, and we're just going to do it again. So let's see what we get here. So the first thing we're seeing this here being C is we see a handful of declarations. It's something we don't do like this in Rust. We do it a bit different. But the thing we need to keep in mind here is, hey, they're actually picking up some values, and I think that's what we saw earlier, right? So priv PCK frec or frequency, and now they're already comparing it. So PCK would be, I would assume, PSRAM clock. I don't know. But let's actually see what we did here. So it was set to 1400, right? So let's actually look at that already. So let's take some notes here, right? Or let's actually define some consts. So we can do it like that. So we say, I don't know, let's use some longer naming here. Clock frequency. We give it a let's use a U32 here. We give it the 1400, and then we don't need the mem size probably. It looks a bit like some memory allocation stuff. We don't do that. We might need page size. I don't know. So a hex OB, that would actually be 11, right? So in hexadecimal, after 9 comes A and then comes B. So that would be 10 and 11 respectively. So we can also write it like that. All right. So now let's get back to this function. So the thing is, we had this frequency hard-coded. Nevertheless, though, there is now some checks on that value, even though it was hard-coded. So we also just hard-coded the value, but we're using a const here. We're not, storing it in a more or less global or, some sort of struct and then reading it out again. I wouldn't know why that would make sense. But it does say the frequency must not be above 300 for whatever reason. And then, depending on whether it might actually be above 1600, whatever, they would set some timing parameters here, and they would be coming from these things here. And it looks like there are some sort of bits defined in a register or something. Let's see. So there is timing control TRC. I don't know what TRC is. Cycle. You know, you see some mask applied and some shifting here. This is shifting by 0, so that doesn't actually change anything. So it's really just the last hex FF bits. So it's the last 8 bits, if you will, right? So the mask FF would mean the lowest 8 bits are actually set to 1. So let's have a look at that. So the bit mask hex FF actually looks like this here, right? Everything above it is just set to 0. All right. So yeah, whatever that means. So we're passing 15 as a value and then applying the mask. Well, or in this instance, 11 actually, because that should be our case here. So it says clock frequency for us is 1400, right? So we're hitting this branch here. So we can already say let timing equals. So that would be 11 shifted by 0, and then yeah, we're ORing it. So we're stitching together some parameters here. So there is timing control TCPHR cycle, whatever that is, and that would be again mask hex FF again, and then shifting by 8. And because that is effectively just 0, we don't need to do anything, right? So we're just not ORing anything here. So we can just ignore that part. Then we get a beautiful 2, and that would be TCPH whatever. Hardware? I don't know. Oh, this might actually be a read and write. Could be. That would be shifted by 16. So we get 2 shifted by 16. And then we get another value, and that was this here, TRFC cycle. That would be set to 18 and shifted by 24. There we go. So it's already saying, hey, this has no effect, right? So yeah, we can just leave it like that. And we might actually want to sort it in a different order, so that we get the most significant part in the beginning and the least significant part in the end. So we will just go like this. All right. And we can actually put a note here, right? So we got this here, that thing, oops, that one, and that one. Yeah, we might need to actually define those again at some point. Yeah, we will see if we actually need that. Anyway, but you can see it's only used in those 3 places. I just searched through the file. All right, and now what you can see here is an invocation of a function that is called writeL. L is for long, and that would be a 32-bit value here. So it's effectively the same thing as our write32 function. And then it's writing to the timing control register. And now the question is, what is the timing control register? Well, up here, we've got a handy definition of all the registers. And we might want to do something similar. So what we're going to do is, we're going to say const timing ctrl or control. For us, that would be a U size, and that would be some base register plus hex 030. And this base register is actually what we saw in the device tree, and I already had that in the code down here. So yeah, let me move that over. That would be the PSRAM controller. So the PSRAM controller, what we're initializing here, starts at the space address. Alrighty. So what we're gonna do is we're gonna write 32, and we are writing to the timing control register, and the value is the timing value. And that is already the first step. And now comes a good bunch of more things. But that would then already hit the end of the function. So yeah, how does it get complicated? Well, it's actually calling into a few more functions here, and that's already the next thing we're doing. So now it's calling into this here, PSRAM analog init. Let's actually do the same thing. Let's define a function, and we call it analog init. I would just skip the PSRAM because this whole thing here is already called psram.rs. And as you can see, it's passing around this thing called priv. So priv would be the thing which encodes the frequency and those like other two values that we saw earlier. So what happens in this function here? Well, it's again calling into another function and then setting a bunch of bits again, and more bits, doing some delays, and that's already it. So effectively, all we're doing here is we're just setting lots of bits in many different registers. And, we just keep going on and on with that until we have, just re-implemented all of that code. And out of a sudden, we have the same thing written in Rust. And that's effectively what we're doing quite a lot to get things running in oreboot. It's an unfortunate necessity. We could technically, create some tools to translate that sort of code. However, I've seen, too many instances of, like fancy vendor-specific macros and stuff like that, where it's no longer as trivial to actually do that sort of translation. And we would effectively actually need a C compiler for it. So, yeah, I do not feel very inclined to actually do that sort of stuff. There is a tool that is called C to Rust or Crust or something. I forgot. And then there is another tool that has just been developed over the last few years, doing a similar job. But yeah, whatever. So yeah, I just wanted to give you a brief impression now of the work we're doing here. And as you can imagine, this is actually pretty boring. The exciting part is when we run this stuff again. So what we can do here in the end is we can do a print, and we can print something like psram init done and smiley face. And that would be it. And now we can run our code just using the make run command again. And I will just need to turn the board off and on again, pressing the boot button. And lo and behold, didn't work. Yeah, I'm getting some issues sometimes with the USB serial thing here. They're actually writing in the wiki even that some are a bit finicky. That might actually be the main cause here. I could use a different USB serial converter. That might actually help. Anyway, we will just rerun it again and be done with it. So yeah, there we go. It worked. And it's writing PSRAM init done. Now it keeps printing lol. And that is really just because in the main function, we actually have a loop that is doing that sort of stuff. We could as well just, I don't know. We could as well just call into, there is an instruction that we can use, which, effectively just puts the core to sleep or something. Well, right, we can call wait for interrupt. So wait for interrupt, is then just keeping the processor busy or something, or, whatever is actually implemented in the hardware. And when it gets an interrupt, again, it would then continue executing, and it would hit your interrupt vector, which we do not have defined here. So yeah, anyway, we're not doing that. We're just staying here in the loop. So yeah, and with that, let's actually fulfill the promise I made earlier and look at the tool that we made. It's called BL808, and it's here on my GitHub. So it's on orange CMS/BL808. And yeah, I will show you a bit of the code that we worked on here. So yeah, on the left-hand side, you see the vendor tool that is called BFLB MCU tool. Yeah, it consists of a bunch of files. That's what we looked at for, actually understanding the protocol and everything, and the many bits that you can use in configuration. And down here, we have the tool that Samuel Holland made, which would load a handful of ELF files. And yeah, instead of reading ELF files, we just read our raw binaries and load them to the addresses that we know. Alrighty, and let's look at the main function here. So in source main RS, that's where we start. We're just using the very well-known clap crate. So clap is the command line argument parser, just has a funny name. We're using that for defining the interface, so the command line interface. We're using, just the regular log crate, and we're using zero copy. So zero copy is a crate that allows you to easily parse and, create structs from bytes and bits. And there is another one that we use. We will actually see that in a bit. Well, and then we have a handful of modules. So we have one that is, dealing with the whole protocol. We have one where we just define a part of the memory map. It's really just two constants in there, actually. Not very much yet. Then we have a module for the ETH uses, and then for, the main boot struct. So the boot structs, as I told you earlier, there is this giant header. There is actually a lot of bytes and bits that we need to fill in there. So yeah, let's have a brief look at that, just to get an impression. And yeah, you see there is a few open changes I haven't yet committed. And that is actually what just enabled me to quickly send the binaries and stuff and run them only on the D0 core, that is the C906 core. They give it different names. Sometimes they call it MM for multimedia core, whatever. So we're only executing code on that one. Then there's a bunch of magics that are being used for configuration in the chip here. We use the CRC module here for the CRC32 checksum. It's this variant of it. So there is also a handful of variants. I had to, see again which one was actually the right one to use. And then, as you can see here, follow the struct. So there is something called flash config. We're just using an empty configuration here. So yeah, we're not even writing the magic. We're just setting everything to 0. And this CRC32 here is actually hard-coded. So yeah, nothing exciting here. Same with the clock configuration. We're not changing anything here, although we actually could. If we wanted to look at those details, we could look at the vendor code again. But yeah, we don't really care about that right now. Then there is a bunch of bits for boot configuration. There is one for the signature, encryption type, keep selection, and whatnot. We're not using any of that sort of stuff, so we just keep everything to 0 as well. Then we're using the SHA-2 digest. Why is that actually down here? Let's actually move that further up here. Anyway, yeah, and as I told you, we actually need to create a SHA-256 checksum, and here is what I described earlier. So you would need to build the hash over each of the segment headers and then the segment data. So we're first setting a whole boot header that includes this thing here called boot config, and then we're sending one segment header, one segment, another segment header, another segment, and that's it. So yeah, I'm not going to elaborate too much on all the details here because, as you can see, it's really a lot, and we have already omitted like tons of bits and bytes here, which we're not using at all. Yeah, this here would be interesting again. So
yeah, there is a configuration for each of the 3 CPU cores. So M0, D0, and LP. LP being the low power core, the smaller 32-bit core. Each of them gets a configuration block, and that's where you actually say, hey, this processor, is supposed to be enabled, or whatever. So yeah, it's this sort of stuff. There is cache configuration in it and whatnot. Yeah, there is this here, boot entry, image offset, and so on. Yeah, that is something that we then actually need to provide when we instantiate it. So yeah, what we always provide is the boot entry. So the boot entry is the address where we have our first byte that we execute, and we just use the start address of the respective memory to use for the respective core. Yeah, which is what we've more or less hard-coded down here. We just have this condition. Depending on whether you want to actually boot the M0 core, we would then provide the address. Otherwise, we would not. Yeah, same with the D0. And we have these two functions here. One is called with entry, that would enable the core and set the address. The other one is new, and that would not enable the core and keep the address at 0, and that's it. Yeah, that's actually what we looked at here. So you see this here, CPU enable and cache. That would get this bit here with config enable. So the with here, that is coming from the crate we're using for creating those structs here. Just means we're now going to make some adjustments to the thing we're instantiating here, so we can just chain a bunch of calls to more of those functions here, and yeah, by calling config enable and passing it a 1, we're enabling it. Yeah, and if you look at this here, you might think that could actually be a small thing, but it's actually a bunch of things. So config enable is actually, I don't know, was it a single bit? I don't think so. I think it should be a Boolean. Right here. Oh no, it's actually U8. So config enable is not just, I think it's effectively 1 bit, but they're still using 8 bits to encode it or something. I don't know. You might find more in the vendor code if you're curious. Yeah, anyway, that is roughly it. But as you can see, this is already 300 lines just for creating a very bare bones header. If you were to set up something like, secure boot and, encryption and signatures and all that stuff, it gets way more complicated. So yeah, this is really just the simplest part. So yeah, that was the boot module here. So let's go back to our main function. The other thing I want to briefly show you is the protocol. So in the protocol, we have a list of all the commands that you can use. So all of these here, we just took them from the vendor code. They might not even be all the commands that are available. So if you look closely here, there is actually certain gaps between those numbers. Yeah, it might be that there are actually more hidden commands. For example, I haven't yet seen one that allows you to just read from memory. I do assume that there is such a command, but I haven't yet found it. There is this command here called change rate. I think it's for changing the baud rate. I haven't yet gotten it to work. And there's another one called clock set. Well, that also is sort of related to the baud rate setting and configuring clocks. Yeah, I'm not yet exactly sure how that works. I thought I had copied exactly the vendor code, but yeah, it hadn't really worked for me. So I'm just ignoring that for now. It's not too crucial for us for the time being. But yeah, as you can see, it's very feature rich. There is a ton of things that you can use. And then the protocol itself is actually rather simple. There's the structure that we need, which is a command packet. So a command packet always has a command and a size encoded. So the command is, the thing that we see above here, just sent over as, an 8-bit value. And then the size is the size of the payload that we send in addition. And yeah, it actually gets instantiated like this.
there has to be, a 0 byte in between for whatever reason. It's, just the way the protocol is encoded. So we just do that. There is a bunch of potential errors that you can get. Again, this here is not an exhaustive list, so there is actually like hundreds of error codes. Those are just the ones I've run into, during the development. They might also happen to you, if some bit gets twisted or something. It's not very likely to happen, but it may actually happen. So you may get this here, right? So you may get a CRC error or something. Another part of the protocol is this here. So for, each and every command that you send, you would then read back again and you would get the status. So the status would be either okay, then everything is fine, or you may get, just 2 bytes encoding FL. I think that is short for fail. And then we would print command failed and then read the code that we saw in the list above, and then convert it to the respective, human-friendly message that we have for it. Yeah, one of them needs a bit of rewording. Anyway. Yeah, and then we actually have 2 kinds of commands. So we have one general function that is called send command, and then there is a function that is called get response. And why do we have the split here? Well, because some commands are just sending over a value, and then they may either get an OK or a fail in an error code, or you might actually send something, you get an OK, and then you would read back a response, and that response, can then contain, for example, if you wanted to read out fuses or you want to read from the SPI flash, those are methods you can use. That would then be the actual data that you would get back. And I can actually demonstrate that right now. So let's run one command that is reading out information. So we say make run, and we would give it the sorry, we're not in oreboot here. We say cargo run. We go -- release, and then we pass it some extra. So first, the command that we use, we're using the info command here. I need to pass the port. So that would be /dev tty USB 0. And lo and behold, we get, it's building again, sorry. Oops, we get an error. So we're just going to try again. Oops, that was... All right. Yeah, it's refusing to cooperate today. Just power cycle everything. All right, that looks better. All right, we just got our replies back. So yeah, what we're doing here is reading out something that is called boot info. I'm not exactly sure what boot info really means. There is a part in it, I haven't yet been able to decode. That would be this thing here. No idea what that means. There is 0808 in here. That could actually be encoding the name of the SoC, BL808. And then there is this here. I don't know, just a 1. Well, then we get some extra information. We get the Wi-Fi MAC, that is the MAC address. We get the package. So the 808C version of the 808 SoC is a QFN88 package. So, that describes like what the chip really looks like physically. So yeah, QFN88 would be like, you've got 88 legs around it, or, 22 on each side or something. It says there is no flash in it. It says version 0. This here is not actually true. It's just that it's, not properly encoded in the fuses. You could put a value in there, but yeah, the OEM chose not to, or whatever. I'm not sure if that is even necessary. There is this bit here, boot ROM protect. Some people were still able to dump the boot ROM. I don't even know what the protection refers to. There is this thing here, which is a bit funny. It's called your log disable. So the MASCRAM actually has a logging function, right? So when it boots up, it would actually log some information and then, I don't know, just write it to SRAM or something. And then there is a log command that you can actually use to read that out. We can also invoke that in a bit. And then, as you can see, there's like tons of more bits in here. There is something called SPI flash pin configuration. It says there is an external SPI flash. I think it was originally serial flash. I need to reword that, I think. Yeah, whatever. And as you can see, there is like a ton more information. Some of that is redundant. So here we're also reading out the fuses, and the fuses are, they're actually, 2 blocks. So I think they were like 128 bits each, or bytes. Yeah, I think it's 2 blocks of 128 bytes, or 256. I forgot. Whatever. As you can see, they're encoding a lot of information again. So yeah, if you look further at the BL boot code, you will actually see all the data structures, and yeah, that will actually tell you a lot more about it. Yeah, this stuff here, I'm not sure. There might actually be a bit of a mistake in here. I'm not expecting any values here. Yeah, I might need to recheck that. Anyway, so yeah, we're reading out all of that information. And now let's actually have a look at the log. So, but let's have a look again. So it said your log is disabled, right? But there is another fuse that you can set, which is called your log reopen. So you can disable the log and then re-enable it, right? So like you can say for production, you don't really want the log to be enabled, but then again, you can still enable it. I don't know. There might be another log bit so that you can actually keep people from re-enabling it or something. I don't know. Anyway, so this is what you read out from the log. So it looks like this here. It says dynamic memory init success. I'm not sure what it's actually doing here. The SRAM, I thought it was SRAM for the C906. It's actually called DRAM in the manual, so it might be related to that. But then again, it's a bit weird here. It says size 0 kilobytes. I don't know. Then there's this here, start CID. I don't know what CID refers to. Then it prints the version of the MASCRAM. So this is like the build timestamp. So it's from September 2021. There is boot mode. I think boot mode refers to now booting over UART or something. I don't know. Then there is ROM driver version. Oh, look at that. Isn't that the same value that we also saw up here? Interesting. We might just wish to call this part here ROM driver version. Interesting. The more you know by just, looking a bit more closely. Yeah, anyway. So what else? We got this here. I don't know. This looks a bit like a commit hash. Could be. ATE pattern not found. No idea what that is. PC or MSP is 0. PC could be a program counter, and that could be stack pointer. I don't know why you would compare those in a way. Then it says 3987, some code for whatever. Boot from IF, I think that is for interface. Then it says EF config PLL. And then it's, printing a bunch of values again, like Xtel, MCU, DSP, EMI, flash, that gives us a baud rate. So this is almost 115/200. It's just a bit off for whatever reason. And now you can see something. So you see it says ACK len equals 8, write memory, len equals 0, get boot info, len equals 4, and so on. And this is actually the commands we're sending over. So, earlier we said we want to get boot information. That would be this command that we sent over. Then what you didn't actually see is we're sending one command setting flash parameters, and that is how we can actually read out some information from the flash part. So for example, we can read the, there is IDs for those flash parts,
and that would encode the vendor of the SPI flash and so on. Yeah, I think this is related, auto scan, flash pin, and so on. Yeah, that is the flash configuration, repower, whatever. Yeah, and those here, those IDs, I think, are to identify the chip in a way, like the internal flash chip. No, the onboard flash chip, so like a SPI flash. Yeah, I think this here is it. Yeah, that is the vendor. Yeah, not sure what this here is referring to. Yeah, this here is like the clock rate used for the chip, and then it's printing this here. It could be, oh, it says read SHA. Right. I think I'm also telling it to read the checksum from flash. I think this is actually the SHA hash that is in the boot info header. Yeah, we can verify that, by looking at a dump of the flash at some point. And then we're reading the efuses. Yeah, here you can see it. We're reading 128 bytes each time. So this is our 0 and our 1. So this is the first block and the second block. And yeah, it's printing the baud rate again, and yeah, that's it. And then it says read log because that is actually the last command that we had sent. All right, and let's now actually do this here. So ROM driver version being encoded here, we will just put that in boot info. So this here is not boot info 0. But we actually get let's make it a 32-bit value, and then let's call it what was it? So something driver version. Whoops, I forgot. ROM driver version. Did I copy that? All right, ROM driver version, and that is a U32. All right. And now let's run the info command again, and whoopsies. Says boot info 0 is not in. What did I mess up? Not found in the scope. Oh, this is actually U32. Right. Yeah, my bad. Alrighty, and now we get the. Yeah, we're just printing a ton of information. Did I not save it properly? I thought I did. Huh. Maybe I just scrolled past it and didn't realize it. No, it says X and then this thing. Oh, I know why. It's because we have a custom print function for it. And we're doing this here. All right, so yeah, we are no longer doing this. We're just doing that. Yeah, I mean, we might as well just say it's a U32. And then, whoops. And then let, I don't know, romdrv equals self.rom driver version. All right, and let romdriv equals format. We're just going to print that value as a, well, 32-bit hex, so we go 08x.
and we will write RAM driver version. There we go. And it looks like this. Oh, huh. Yeah, we just messed it up. So RAM driver version actually comes first, and then comes, you know, just zeros. Now I'm not sure what those zeros are. So the problem is if you have some values that you can recognize from somewhere, that's very, you know, sort of convenient. If you just get zeros, you know, it could be coming from any sort of source. So yeah, whatever. Oops. Let's see if we get this right now. Yeah, beautiful. RAM driver version. Yeah, I would assume this is actually encoding the BL808 here in a way. Anyway, we're just printing the same that the vendor is printing when it was saying RAM driver version. Beautiful. All right. Yeah, that was the aux64. You know, a bit of a closer look again today. And what might be interesting to you, we also worked with a different SoC and board some earlier. And that was the, well, the board was the Vision 5.2 and the SoC would be the JH7110. And that is where we had already run into the so-called fuses or OTP area. So OTP is one-time programmable. It's, you know, sort of overlapping terminology. And I was actually asking the vendor Star5 to, you know, provide information on that. So how do those fuses work? How would the secure boot flow work? And unfortunately, there has been no answer so far. And what I've done though in the meantime was, you know, I've taken the Mascrom and also, you know, worked a bit on my own tooling to, you know, reverse engineer a bunch of that stuff. Now I've taken a bunch of notes in here. And, you know, I've created my own tool to, you know, create a header for me that would already encode a bunch of that information. However, I couldn't get to a sufficient point. So, yeah, it's not yet complete, unfortunately. Yeah, and that's why, you know, if you're an SoC vendor, we really need your collaboration here. Yeah, otherwise, you know, that is all we can do. And that is actually very sad because there is a bunch of people in the community who would really like to do awesome and cool stuff with your chips. And, you know, those are your customers, actually. And that is, you know, also true for everyone in the industry. If you have B2B customers, they would also like to do something with your chips. So they also need a lot of documentation. Anyway, yeah, back to our beautiful board here. Again, that was the aux64 from Pine64. Yeah, thanks again for the gift. And yeah, I'm looking forward to actually meeting a bunch of people again at FOSDEM very, very soon. And yeah, thanks to everyone watching here. Have a good one and see you another time.